Number 22. A uniform beam of mass m is pivoted at one end and held in equilibrium at an angle theta by a horizontal wire as shown above. Tension T in the wire is. Alright, so let's draw some forces here. There's a tension T in the wire, and there's also a gravitational force mg. Right? And this is theta here. Alright? So if that's theta, then this is also theta. And then this, the angle between the beam and the gravitational force, is, notice that's not theta. That's the complement of theta. Okay, so the net torque, if I take this to be the axis, the hinge is always a good place to make your axis, then I have two torques that must be balanced. I have a torque of T times the full length of the thing, right? This is my FR sine theta, times the sine of the angle between them. That's got to be equal to the torque from gravity, which is mg times, it's acting at only half L, so that would be L over 2, times, now I can't say sine of theta because that's the wrong angle here, but this angle, if you remember that the sine and cosine of complementary angles are equal, so the sine of this angle is equal to the cosine of its complement. So that's cosine theta. You can do some trig there to figure that out. I need the perpendicular part of that, so that's going to be the part that is adjacent to that theta angle. Okay? And then the L's cancel. And I want to know what T is. So let's see, T, I'm going to divide that over to the other side. So I got mg over 2, and then cosine divided by sine, that's cotangent. So it looks like 1/2 mg cotangent theta is correct, part A. So here, a gear containing 20 teeth on its circumference is meshed with a gear containing 60 teeth on its circumference, as shown. If the angular velocity of the 20-tooth one is omega, what's the angular speed of the 60-tooth gear? There's different ways to deal with this. One of them is to say that, well, the r of the, since circumference is equal to 2 pi r, that means circumference is directly related to r just by a constant of 2 pi. So that means if this is 20 to 60 radius, then if the radius of this is r, the radius of this must be 3r. And I know that omega is equal to v over r in general, right? And I know that as these teeth go by, the v's are the same, right? Same v. It's like the belt that goes around things, or a cord that goes over a pulley and around something else. The v is the same because of the way they're interlocked there. So that means that the I could say v is equal to omega r. So the omega r's have to be the same. So if omega for the small one times its r must be equal to omega of the big one times its 3r, that means omega big, if I divide the 3 over, is equal to omega over r. I think you'd also probably do that one just by applying some common sense. As if there's 60 teeth on that, then in the time that this makes one full revolution, this goes through 20 teeth. There's 20, and then another 20, and then another 20. So this one, in the time this goes all the way around, makes a full revolution. This only makes a third of a revolution. So you could kind of think about it like that, too. Number 24. The angular displacement of a rotating wheel is described by the equation this. So this smells of calculus, doesn't it? Where t is time and theta 0 and a and b are positive constants. The angular acceleration of the wheel is a function of time. So that would be this angular position, so I need two derivatives. So omega would be the derivative of this. That's a constant, so that goes away. So there's my first derivative, and then angular acceleration would be 2a minus 6bt. Geez, that's easy. If you know how to do calculus. 25 through 27 refer to this: velocity versus time graph. Motion of an object moving along a straight line is described by the graph of velocity versus time above. Which of the following is true about the speed of the object? Speed, that's absolute value of velocity, during the time interval from 0 to 8. So the speed, it starts out with a speed of 2.5, right? That's absolute value of velocity, decreases to 0, and then increases up to 2.5 again. So, no, no, no. It first decreases and then increases, right? So you have to be tipped off that this says speed here. Think absolute value. That is important. Which of the following is true about the acceleration of the object during the time interval? Well, the acceleration is just the slope of this. So it's the same. It's the constant slope of that line. Right? Number 27. What is the net displacement of the object? Well, displacement is area. So from 0 to 8, I have this negative bit and this positive bit, so the net displacement is 0. Wow, that was easy. 28. An object starts from rest and accelerates uniformly in the horizontal direction, moving 32 meters during the first 4 seconds. What are the magnitudes of the object's displacement and velocity after it accelerates for the first 3 seconds? Are they missing a question mark here? That's weird. They don't usually make mistakes like that. So it starts from rest and accelerates uniformly. So a constant a, that means I can use kinematics. Yay. 32 meters during the first 4 seconds. Okay, so let's do a little kinematics here. So figure out what that acceleration is. So it starts from rest, goes 32 meters in the first 4 seconds. Right, so the acceleration, let's see, that's going to be delta x equals 1/2 at squared plus vi t. The vi is 0, so delta x is equal to 1/2 a times t squared. So it looks like that's 2/2 of 16 is 8 divided by, so that it looks like the acceleration is 4. Okay? Now they want to know what are the magnitudes of the object's displacement and velocity after it accelerates for the first 3 seconds. Well, now that we know that the acceleration is this, we know that after 3 seconds it will be going 12 meters per second. Right? 0, 4, 8, 12. So it's got to be one of these two. So I can just figure out then, new kinematics problem. If you start from rest and you go for 3 seconds with an acceleration of 4 meters per second squared, how far do you go? And that, once again, is delta x equals 1/2 at squared plus vit. That's gone. So how far do we go? 1/2 a t squared. That's 2 times 9. So that's D. 18. Let's see, maybe one more in this video. A 2-kilogram cart rolls with negligible friction on a horizontal surface, as shown in the figure above. The coefficient of static friction is 0.7. Can't have more friction than that. If a horizontal for 15 Newton force is applied to the cart, as shown in the block, does not slide, the magnitude of the horizontal component of the force that the block exerts on the cart. So block exerts on cart is the same as cart exerts on block, and that is the frictional force. Right? The horizontal component, rather. Of course, there's a normal force, but the horizontal part, that is the frictional force. So this is a static friction problem, and that means we can have up to this much friction. So let's see what's going on here. First of all, let's figure out what the acceleration of this is. If I've got 15 newtons accelerating a total of 3 kilograms, the acceleration is 5 meters per second squared. Now that means that there must be here on this block, what's accelerating that block? Let's make a force diagram. So there's there's G, mg, 1g, whatever, and then there's the normal force, and then there's the frictional force, which is the only thing that's keeping it going, right? So that is the net force on this block. So the net force on this block, which is just the frictional force, is equal to its mass times its acceleration. So there has to be 5 newtons of frictional force. The only thing that would remain to be checked is it possible for there to be that much? What's the maximum amount of friction? Well, the normal force here would be equal to mg. The normal force would be 10 newtons, right? This times 10, and that times 0.7. So you can have up to 7 newtons of friction. How much do I need? To get it to accelerate like this, I need 5 newtons of frictional force. That's B. A car runs a flat curve of radius r with a speed of v sub 0. Coefficient of friction between the tires and the road is mu. For the car not to slide on the road, which of the following statements must be true? So we're talking about a car. If we're looking at the car, and the car is going into the page, and it's going around the turn this way, then there must be a force toward the middle, right? There must be an unbalanced force toward the center of the circle. So that comes only from friction, right? Friction between the tires and the road. This is the mass of the car, m times g. That would be the gravitational force. Normal force is also mg. So the frictional force is mu mg, right, toward the middle. And since that's the only force toward the center of the circle, that must be equal to mv squared over r. We call that v sub 0, whatever. So doing a little work here, let's see. The car speed, so this is max, right? So here, let's say this. You can go slower than this, but if you want to max out your friction, set your velocity maximum, then you would have v max, if we solve for that, is equal to the square root of mu g r. So let's see what we can figure out here. It looks like they're kind of twisting this around in some different ways. The car's speed cannot be greater than mu gr. Well, in fact, it can't be greater than the square root of mu gr, so that's no good. Car's speed v sub 0 cannot be less than mu gr. Well, mu gr is actually not the boundary at all, so it can be less than that. Of course, it could be 0 or very slow, and you'd be fine. The radius r of the car's path cannot be greater than this. Okay, so let's see here. So if we solve this for r instead, then I would get r is equal to, and now this is the maximum, but if we were going to mess the maximum velocity, if we're going to mess with the radius, making the curve have a smaller radius is going to make it more dangerous, basically, right? So for the car not to slide off the road, making the radius smaller is more dangerous. So the radius being bigger cannot be greater than. You could make the radius, 1,000,000, and then basically it's a straight road, so there's no problem. So radius being less than is an issue. The centripetal acceleration is less than g, so let's check out these last two. So if you want to find the minimum value of r, then that would be the same as solving this. R would be equal to v over mu g. sorry, v squared over mu g. So that would be the minimum radius, so it cannot be less than, so this looks like it's correct. And then just quickly here, the centripetal acceleration must be less than g. I think that doesn't include the mu in it anywhere, so that's not very helpful for us, right? The centripetal acceleration, which is v squared over r, is set by a boundary at mu g, not just g. Alright, that's a little tricky. If two balls collide and there are no external forces acting on the balls, quantities that must be the same for the two-ball system before and after include which of the following? So they collide and there are no external forces, but they didn't say that it was an elastic collision. They didn't say elastic. So they collide and we don't know anything else. So kinetic energy, that does not need to be conserved unless they tell us that it's elastic. Momentum, that must be conserved. And then momentum in the x direction is also conserved. If you break up the components, you have to have conservation of momentum in every dimension. So 2 and 3. Is true. You can't have this one, total momentum conserved, without momentum in the x direction, right? It's an independent. You could just look at the x direction, just look at the y direction, and work like that. So the answer is D. 31 is D. 32. Two objects, x and y, are released from rest at the same height. Object x has 3 times the mass of object y. Just before reaching the ground, object y has momentum py and kinetic energy ky. If air resistance is negligible, what are the momentum and kinetic energy of object x? So let's see. Object x has 3 times the mass of object y. So since momentum equals mass times velocity, they're going to be going the same speed when they hit the ground, right? Because air resistance is negligible. So that means the p of the bigger one is just going to be 3 times more. Right? And when the kinetic energy is equal to 1/2 mv squared, but they have the same v, so tripling the m is only going to just triple the kinetic energy also. So that's some proportional reasoning there. You're only changing the mass, and both of these things depend only linearly on mass. Okay, that's B. It's almost there. Numbers 33 and 34. A very light ball is released from rest at time 0 and falls through the air, which provides significant resistance. Which graph best represents the magnitude of the momentum of the ball? Now, momentum is equal to mass times velocity. So whatever the momentum graph looks like, it looks the same as the velocity graph, right? Just m times v. It's just like changing the scale here. So basically, if that helps you think about it, these are like looking at velocity graphs, right? Same difference. And likewise here, magnitude of the net force on the ball, that's like looking at acceleration graphs. And I think that that's maybe more familiar. So let's do that. It's released from rest and falls through the air. So it's going to start, it looks like down as they've taken down to be the positive direction here. So it starts with 0 velocity, and then if there's significant air resistance, it's going to reach a terminal velocity. So it starts from 0 and approaches a terminal velocity. That looks like D. That's what we expect those graphs to look like. Now the acceleration would start out at 9.8 and then get closer and closer to 0, because at terminal velocity this flattens out, so therefore the slope flattens out to 0. We've seen those graphs a few times, so I guess if you get the P is the same as V and F is the same as A business there, I hope that that's fairly straightforward. And last, satellite can move in a circular orbit about a massive planet of radius r. Which of the following could represent the gravitational potential energy U of this satellite as a function of the radius r of the orbit? Well, gravitational potential energy is equal to negative g m for r. Right? So that looks like, this is all a constant, so it basically looks like a graph of a function of the form negative 1 over x. And that looks like this. Right? 1 over x looks like this. And upside down. It's like that right there. And that's it. Why does it stop at r? Well, at r, it's at the surface of the planet, so you can't go, I mean, you can go inside the planet, and in fact, pause the video and try to answer this question. If you completed this and you had a tunnel that went inside the planet, then what would the rest of the graph look like as you approached 0 radius? Pause. It looks like this. And we looked at problems of this type. I'm not going to go into in the video here why exactly it looks like that, but it has to do with the fact that when you're inside a spherical shell, the gravity that you feel is only the gravity of as if you were on a planet that was only had a radius of that much, right? Everything that's outside where you are at all cancels out and has no net gravitational effect on you. Oh. There you go.